This morning we have Dr. John Onofrey, who's Assistant Professor of Radiology, Biomedical Imaging, and Urology, and he's going to be talking about application of machine learning to prostate cancer in urology.
So good morning, everyone. Thank you for inviting me, and I'm looking forward to presenting some of this work. The main focus of this work is really machine learning and how we have applied that really to prostate cancer and applications in urology at Yale. So in particular, I'm going to be focusing on what has been done here and not really just giving an overview of what else has been done elsewhere, because it's a pretty broad field and there's a lot of application and very exciting area. So to start, my only disclosure is that I'm the PI of an NIH grant, of which we are a sub-award from Eigen Health Services, and Eigen provides the Artemis prostate image-guided biopsy system that we have been working with for research purposes and used in the clinic here at Yale. So brief outline of what I'm going to discuss. I'm going to start with a pretty general overview of what machine learning, artificial intelligence is, and one of the biggest buzzwords in probably the world right now is deep learning. This has kind of taken over all forms of commercial entities and computer science, and it's really become the hot topic. And now people are applying it to everything. And that's what I'm then going to transition into, is how we have used this technology to prostate cancer and in other applications in urology. And finally, I'll just conclude with some thoughts about machine learning in medicine in particular. So artificial intelligence, this is really a big word that you may hear used a lot. And it seems to get confused with these other terms of machine learning, deep learning. So really, this is just kind of a nomenclature here to separate it, that artificial intelligence is the overarching concept of what people ideal to have humans mimic human behavior, or computers mimic human behavior. But machine learning is really the hardware or the tools that we use to do this kind of learning. And deep learning itself is really just a subset of this. And the main difference really is that with deep learning, you let actually these models, these deep learning artificial neural networks kind of learn from the data exactly what you're interested in, the features themselves. Whereas in machine learning, this was kind of a problem of feature engineering. And I'll get into kind of the details a little bit of what distinguishes these. But really, this just sets the stage for where this all fits. So really, in terms of anything that you see applied in healthcare, though, it's really going to be machine learning. We are nowhere near artificial intelligence. There's nothing intelligent really about what we're doing. It's purely just computational models, mathematics. And so artificial intelligence is my personal belief right now. It's kind of more relegated as like a marketing term. So when you come across it in papers or anything that you see, you can probably bet that the marketing team probably got a hold of AI and started using it, slapping on top of a product. So the main things in any kind of machine learning that we're really looking to do is these supervised versus like unsupervised learning. So it's really split into two different kinds. And for the most part, I'm going to be talking about supervised learning here, but just to kind of illustrate what we are actually looking at here is that these tasks do different things. So in the supervised learning, what you have is you have a bunch of points. Now these points just represent data samples. These can be anything. So just for example, they are represented by dots here. But in supervised learning, you actually have a known label. So in your case, a clinician, probably annotated this data to say that group A was different than group B. In classification, what we're interested in doing is pretty much finding some way to divide those two sets of data. So in this case, this is just finding a line that separates these two classes. So that would be an example of machine learning doing supervised learning in a discrete sense. So you're just trying to say, what is the line that divides these two sets? Now, a little bit different is regression. A regression form of supervised learning. Now this is something akin to like fitting a line, a best fit line of your data points. So what this allows you to do is basically extrapolate what the values would be from these points at other points that don't exist. So this is something like as simple as just fitting a line to data points and then saying it's the best fit line that minimizes some error. And that allows us to, do some kind of predictions on it. So this is different in that it's a continuous value. You can predict anywhere on this line. Whereas in the discrete sense, previously in the classification, you're only on either side of that line. It's a yes, no, almost a binary in this case. Unsupervised learning is different. In this case, we don't have like a human to tell us what is group A and group B. Instead, we rely on some kinds of like modeling to try to find clusters within this data. So that could be finding a cluster of A and a cluster of B. And this basically just gets formed as, well, you can say, oh, this cluster exists, this other cluster. Now, this is discrete because, well, we say, oh, we're going to find 2 clusters in this data set. You kind of have to know that ahead of time. Whereas something in the continuous domain in this unsupervised learning is something like dimensionality reduction. Now here, this could be something like finding a principal component analysis of this data. So what this says, I'm going to find the principal directions of which this data exists. So if it looks like it's primarily has this upward trend, well, that's going to be my first principal direction, and this will be my second one here. So the data most changes along these 2 directions. And what this kind of analysis allows you to do is you can transform this data into something that is hopefully a little more interpretable. So that's just represented here by like rotating this. Now you have this, while it's 2D data points here, well, I'm rotating this and then I can find, oh, well, this varies mostly along this one direction. So you're really reducing it down into just a single dimension or something if you wanted to. But this is another form of unsupervised learning where the data is telling you what is of interest. And since I come from an image processing background in radiology, I like these graphical examples to try to illustrate which each one of these things really is. So like I said before, really focusing on supervised learning in this case. So taking these 2 examples of radiology images, a form of classification would be, well, is this just an image of the brain? This is simply just assigning a label. Well, is this MR image of the prostate? That would be classification. I'm doing it into 2 separate sets. Regression form of this problem could be something just, silly examples. What is the age of this person given their brain image? So you see, this isn't a discrete value, but rather it's some kind of decimal value here. The other one is, for example, just some form of cancer risk given this prostate image. And these things could be like these continuous valued functions, of course. But again, this would come from like labeled data, something that you had like lab values to back up. Now, another form of classification, like really in the imaging domain as well, can we label parts of the images into very specific subregions? So for example, in the brain, there's the Brodmann areas. It can be parcellated into subsets. Or in the prostate, it could be just aligning the whole prostate gland itself. And so this is really just a form of classification though, but it's classification on every single pixel in the image. So everything that there gets assigned to a label. And again, just to reinforce this, that this was anything that was done here, it's supervised. That means somebody had to tell the algorithm what these kind of things were. So this requires manual annotation. So finally, anything in supervised machine learning really fits within a certain general framework. So how does someone start from basic data, labeling it, and then how do you train a machine learning algorithm to deal with that? Well, there's your input and your output. So for example, I'm going to look at this segmentation case here, this classification. So given these labels of this brain image, how can I train a model to give me this result? Well, I'm just going to start with this abstract concept of model. It's basically think of it just as a black box in this case. Inside that black box, there are a bunch of parameters that can be set. And so we're going to set that in basically a loop. So that loop needs to be told whether you're doing a good job or a bad job. So this progresses in a very iterative fashion. So it goes along, it starts from nothing, and then it slowly builds up to hopefully the correct answer. So this objective function measures how well you compare to your ground truth. And the way that you evaluate and then keep actually training this model is that you have an optimization. So this thing basically adjusts what is inside the model, the values, and it refines those values so that you're able to get closer and closer to your training data. Now, the goal is that you train these models and then it will work well on data that you haven't seen. So that's really called like the test set. So you have a set of training data and then you have test data. So that is really the basic concepts of machine learning. And now I just want to quickly dive into what is deep learning. Deep learning in particular, as I mentioned before, has really been the hot buzzword. And it has just exploded, really. And I can't possibly do justice to the topic in the time here. So I would highly recommend, if anyone is interested in getting a pretty good overview, very limited math in this one, but it's a review of deep learning by pretty much the three godfathers of deep learning. And this appeared in Nature a few years ago. So it's a pretty great article, and I highly recommend checking it out to get some good understanding and some good visuals of what it is. But I'm going to try to do my best at showing what it is in a very short amount of time. So as I hinted at before, in any kind of machine learning, what happens is you're kind of trying to learn something about the data that gets me to the answer that I desire. And that involves trying to learn features of the data, like what part of the data tells me that something is important. So for example, in images, this could be edges or groups of edges, or it could be some kind of the colors that are involved. And traditionally, this came from human feature engineering. So people would say, oh, I want to look at this color in an image, and that will tell me that this one is a brain. Or if you have more of this other color in your image, well, maybe then that's a prostate image. But in deep learning, you really let the data decide what those features are. And it basically, it allows you to build up this hierarchy of information. So it's not just a single color, but then it becomes groups of colors or edges, and groups of edges become like whole parts, and then parts become parts of larger like groupings. And so this has been around for a long, long time, actually. So it started all the way out, really the beginnings became all the way in like 1952 with like this gradient descent, and that's a form of optimization. The initial work was in these perceptrons that were really the precursors to artificial neural nets that we know of today. And the tools that allowed this to happen was something called backpropagation. And that's what allowed like the training of these things to happen from your end label to your input. You have to go backwards, actually. And the idea of these deep networks, and I'll explain what those are in a second, really was from 1995. But the real boom in this space took off in 2012 from this one particular paper that utilized this form of neural networks called convolutional neural networks and outperformed all other models at the time in this one particular image challenge data set. Now, this data set was basically something like, given a set of images, can you predict whether it had something like 10 classes in it? So a cat, a dog, a bird, a house. But this thing was really responsible for making like a quantum jump in performance that never had been seen before. And ever since then, we haven't looked back in deep learning. Pretty much everything else has been put by the wayside in favor of just pursuing deep learning. So why the explosion in 2012? Well, first is probably the availability and access to big data. It's really, the internet has allowed a lot of large sets of data to start existing and being shared. And just the sheer volume of these images that were available are critical for training any of these deep learning models. They are very data hungry. And so by that being available finally, well, now they actually became practical to train and become useful. And the second is hardware. So really what the thing that drives this is a lot of small computations. And that really comes out of these like graphics processing units that you'll find in all of our computers. But these GPUs really took off mainly because of like the gaming industry and graphics driven within personal computers. So these things became powerful enough. They have enough basically mini computers on board that you can perform a whole bunch of parallel computations. And this allowed actually practical training of these deep neural networks. And then finally, there is the prevalence of open source libraries that made building of these deep neural networks very feasible, very practical. Now, essentially, it doesn't actually require so much knowledge of like feature engineering or anything. It's more programming. It's putting building blocks together. And this is actually fairly simple. You can get pretty amazing results without having much domain knowledge or expertise in the data itself, and not even being like a professional programmer. These are that simple to use. It's pretty great. And there's been a lot of consolidation over the past year about what are the two big libraries now. And they're led by TensorFlow, which is supported by Google, versus PyTorch, which is supported by Facebook. And they're kind of merging towards each other now. They really do almost the same thing. They're both pretty great. But if anyone's interested in picking them up, they both use Python as a language, so it's very interpretable across any computers, and it's very simple building blocks to use. So all of this confluence of all these things has really led to the boom in deep learning. So the basis of deep learning, though, comes from artificial neural networks. So these started out, they're loosely based on the ideas of neurons in the brain. So you have a bunch of inputs going in, and it comes out as some form of an output. Well, mathematically, this can be represented as like a graph. So where we just make the inputs as variables x, and output as something like y. And well, those links that connect that are actually the weights. So these weights can form basically a mathematical equation. So whenever you're training these kind of networks, well, what you're doing is you're actually learning these weights. This B term is a bias term. So if I was given a whole bunch of Y's and a whole bunch of X values, well, I would train this thing to find the values of W. Basically, I would try to find the values of this W1 and W2 that try to give me the best set of answers that match for whatever training data I have. So this is, in this one slide, this is kind of how these networks came about, the intuition behind them. It's very loosely based on them. So this obviously is not deep. What is deep then? Well, deep is just taking that middle layer and actually making a lot of layers in between. So rather than just having one set of weights, W, connecting my inputs X and my output Y, well, now I have a whole bunch. And actually these ones have a bunch of interrelationships between them, and then this just fits within that overall model that we had before. So this just fits in this training loop, and all you are learning is these middle weights in here. And now typically these are called hidden layers within this network. And that's really all that there is for deep learning. And people have gone to extremes to start stacking as many hidden layers as possible into these deep neural networks, because the intuition is that the depth, more deep, gets you better results. And that comes at the cost of course, computational cost, but some people have gone to extremes of putting over 100 layers in these things. And these things are really just as simple as those those multiplications and additions of those bias terms, and they come in a various different things, but they also, the cookbook basically includes these things called convolutions, activation functions, pooling, normalization, the details of which you could probably find in that, that review paper. But really, this is the entire building blocks of deep learning all into this. Of particular interest in imaging, since I have such a background in this, are these convolutional neural networks. And the way those operate is, rather than just having a fixed weights, well, those weights can actually move around, but these weights are shared. So as you move around, you operate on the image, and you actually can like apply that same filter, those set of weights to different parts of the image. And in that way, you're able to build up this hierarchy of representation that's in the spatial sense. So again, this was inspired by a lot of neuroscience work of the visual cortex. And here you see that one paper again that really was responsible for the boom in deep learning. To kind of give a visual sense of what this learns, so I keep talking about features, well, it's kind of like this abstract sense. This actually shows what like these filters would be, these features. So this is example of like this particular network was, it was trying to learn just from images, 2D images of cats and dogs. Well, it trained over millions of images. And this is what it basically turned out, these little building blocks that look like actually edge detectors. And this is very similar to what you see in primate visual cortex studies that were kind of the inspiration for this. So these things will actually go across images like this, and they'll respond to edges in the image. But imagine if you do this in a hierarchy, well, you start getting the edges again, and then you get groups of edges that form curves, and then other ones form like whole parts of the image. So that's what allowed this feature, this network, to say, oh, I'm going to find a dog in that very well. And here is actually an example in the hierarchy of what that looks like. So given the input image here, you have this dog. Well, that filter it operates on, you can kind of see what it picks up here is that it like actually finds features such as the eyes, bright spots are saying, oh, that's a response. But it does this in this hierarchical manner. And what it does actually is spits out what it thinks that is in this picture. So you could see the highest scoring class that it thought it was a Samoyed, a type of dog. You know, you've seen another egg. I think that actually is a Samoyed puppy or so. But it also thought it was decently a Papillon there, or a Pomeranian, or an Arctic fox. You can see why those ones are fairly similar. They're all like fairly white, fluffy type dogs. And various, I guess these are all some kind of dog-based classification, but gives you the example of what it's trying to do. Now, this has been applied, we've applied this to a lot of work at Yale, and all of this has actually been done with almost the very same network architecture. So, for example, in A, this just shows prostate segmentation, the gland. So putting an image in, and we were able to get the segmentation of the prostate gland out. This one is showing identification of the human brain in CT images. And this one is interesting because it has a lot of artifacts involved. So it was more, cases with pathology involved. That's very difficult. That's not like normal anatomy, especially parts of missing brain. Another one is just finding mice brains inside MRs of mice. And this one was interesting because we only had two subjects, two mice for training data, but it's actually worked decently well because they're genetically similar mice. So it's almost like retraining with the same subject, and it worked fairly well. All three of these first examples were just examples of binary classification, where you're just trying to say, oh, I have one object of interest and I want to distinguish it from the background. Well, you can also try to identify more than one object in any given image. So this one is an example of trying to find different tissue classes within the brain. So this one is just brain soft tissue, then there's cerebrospinal fluid, and then bone. And it is a pretty decent job. Another example is in X-ray imaging, trying to detect fractures and metatarsals here of the foot. you could see that the algorithm in the blue did pretty good compared to the red, which was the ground truth identified by a human. So a form of regression here was actually generating, given an MRI image of a patient, can you synthesize, can you predict what that person's CT image would be? Then the motivation for that was, well, I don't want to give everybody a CT because it has ionizing radiation. Can I just predict what that CT image would be? And so given a whole bunch of matched MRI and CT, we're actually able to predict what that particular person's CT image might look like. So in hopes of that person, maybe they need to use a CT image for some other downstream processing, but now they don't actually have to get a CT. They can just get their MRI and be free of ionizing radiation, and then we can just synthesize what that one would look like, and maybe it's good enough. Another form of segmentation here is classifying these regions of interest in mice hind legs here. So what this shows is that the areas that were identified automatically corresponded enough to human raters that manually had to do this painstaking manner, that the final downstream calculations correlated almost perfectly with like 0.988 correlation value. So it does a good enough job that it's at human level rater performance, so saves hopefully some people a lot of time. And then PET imaging has also been applied as a form of like denoising. So the goal in PET, again, to avoid more radiation exposure, well, you can reduce the amount of radiation, tracer that a patient receives to about 1/10 of what they normally would get. And you get this really crummy looking image. But through deep learning, you can actually try to synthesize or predict what that image would look like if they had been given the full dose of that radioactive tracer. So again, it's kind of like a risk minimization or a harm minimization there, trying to reduce dose but get as high quality of an image as possible. And it was really amazing, again, just to reinforce that this was all done pretty much with the same form of network. So now I'd just like to go into the applications that we've been able to do with prostate cancer and urology. So I really broke this down into about 3 applications that we've identified here, or started working on. These were kind of the lower hanging fruit. And within this whole kind of pathway of prostate cancer care, we've kind of attacked these 3 parts so far. I'm saying so far because I'd love to have ideas for how we can do the rest of these. And I think there's a lot of interest here. So first off, look at some of the work that we've done in automating like radiological reporting. And this is a form of classification here. So in this sense, we're trying to actually mimic what the PIRAD system tries to do for the standardization of prostate cancer. So PIRADS is good, it provides some identification, but there's a lot of variability in it. So there's a lot of motivation to try to do better, to try to do this more consistently. And this is also used for further downstream processing in that prostate cancer care pathway as targets for image-guided biopsy. So the first task, and this was something I hinted at before, was, well, do you put in a T2 weighted MRI image, and can you identify the prostate? And this has been a heavily researched problem because it's fairly well studied, and it works very well. Another thing, while this isn't actually machine learning, but a pre-processing step that we've done was, well, you have typically a set of multi-parametric MRI of the prostate. And currently radiologists, these things are all acquired at slightly different times during the scanning session, and the patient moves. So there's this kind of misregistration between the anatomy, and also these images are acquired at different resolution. Radiologists currently rely on doing this alignment of the prostate in their head, and that results in these discordance among where you actually think the lesions could be from one image, for example, in the ADC. It is hard to localize that same within the T2 imaging. So one thing that we've done was used automated image registration to align all of these images to the T2 image itself. So you can see the result. These all look like they're in pretty much the same space. And we quantified this, how well it works, compared to a bunch of raters. We had 3 radiologists actually go through and mark landmarks in each of these, and each of those modalities. And what we saw is that our error in the registration is actually less than the localization error between those different radiologists. So as a pre-processing tool, aligning all these images to one really seems to work well. And in terms of the methodology, it's pretty successful. Now the goal is to use this as further downstream processing too. So rather than using just the T2 imaging itself, well, now we can use a whole bunch of correlated images that are aligned within the same space. A more recent one that we submitted as another NIH grant is to actually subdivide those prostate gland segmentations into the 38 regions of interest that are defined by PIRADS. So this specification parcellates the prostate gland into a bunch of smaller regions. And so far, this algorithm, it does a pretty good job. Now, this top row corresponds to the ground truth. That was a human manual segmentation that took something like 4 to 6 hours to do this by labeling every single voxel according to some region. And then we're trying to automate that process by fitting this template to match that. And in some cases, I think this one almost looks a little bit better. It's a little bit more standardized, less, it's more free of these kinds of, I don't know, nonlinear region things. And we're able to actually get, so for example, the peripheral zone, we can get about 85% of the overlap between the automated result and the manual segmentation ground truth. So we think we're doing pretty well on that. And then this other one is above 90% of just basically it's peripheral zone and not peripheral zone here. So it's the rest of the gland. The next component of this radiological interpretation is automatically detecting lesions within this. So for example, here, we're able to use these very similar networks to detect just lesions within the T2 MRI by itself. And this one shows it does a pretty good job finding lesions within the peripheral zone in particular, because that's what shows up really well in this T2 imaging. And it does a pretty good job. Now, the main thing that we're limited by is that PIRADS itself is fairly subjective. So we're going up against ground truth that is fairly, has fairly high variance in there anyway. Next, something that we've been doing for a while has been working with Dr. Sprenkel, trying to improve the actual biopsy image-guided fusion process. This is a form of actually this is the unsupervised case where we're doing dimensionality reduction, actually. It's one of the rare times that we've used that. So in this procedure, this part, the patient comes in having had MR imaging. Well, then they want to actually try to biopsy where the targets that were identified in the MR were, using under guidance by ultrasound imaging. And the way that happens is the prostate is segmented manually by a radiologist first. And then during the biopsy procedure, the prostate is again trying to be segmented by the urologist. And then what happens is those two surfaces that are created are aligned. They are fused together in some kind of registration process. Well, the main challenge here is that actually that ultrasound segmentation process is fraught with error. This is basically a quantification that we did. So Dr. Sprenkel painstakingly went through about 100 prostates and segmented them not once, but twice. And we found like where the errors actually were. And so you could see that there's a lot of error down here where there's less image contrast. So it's down around the base area, I guess. And this makes sense. That's just where the signal in the ultrasound is not. And that results in misregistration or misaligned fusion. So what we proposed to do in this work was actually model how the prostate would deform between the MR imaging and the ultrasound to kind of compensate for having those kind of errors. And so that just, in this video, it looks like this. This is actually a model of deformation using over 100 patients from Yale. And you can see the main, this is a principal component analysis, the main component of this deformation really seems to be, it corresponds to about the insertion of the ultrasound probe and kind of squishing the prostate, deforming it. And so that's really interesting, is that by constraining the problem, predicting it to have moved in this way, you can actually get more stable fusion results as measured by like landmarks. So by having landmarks that could be found something like a cyst in both the MR and the ultrasound image, you're able to find like the error of that fusion process. So what we found was this deformation model has a median error much less than the current method that's used by the system itself. So what you're seeing, this one has such a large error bars because it fuses, it misregisters to the errors that are in that ultrasound segmentation. But by learning this dimensionality reduction, you constrain your problem so you don't overfit to those errors. And that's really what you're also seeing here. This is simulating that error. You could see that here is the standard kind of this standard fusion process, very susceptible to error. But as you add, as you have this deformation model, it is actually very insensitive to the errors that are added to it, and it performs very well. And this was actually very interesting because this was a software solution to this problem, and we actually ran a prospective study to see how this does. So this was very interesting because I would go into the clinic with Dr. Sprenkle sometimes. After a few kinks, we got it to work out much faster, but I would stand there with a laptop and run this alternative fusion algorithm, and then we would show the results live on the on the Artemis machine to show the difference between the two predicted regions of interest versus the original Artemis ones. And in some cases, you would see very different results. So the orange ones are our predicted results here. And so like this case, you could see it's very different from the blue, which was the standard fusion approach. It's very interesting to see where these cores actually correspond to in those. So recently we're actually trying to quantify like, well, what did this core actually hit something that we predicted versus where the other one was? And does that explain some of the discrepancy between pathology results? Is it really a sampling problem when you get some pathology that you're not expecting, like where you expected to find cancer and you didn't, or vice versa, you didn't expect cancer there, but then you did find it. So looking to quantify this in the future is going to be very exciting. But the fact that we were able to actually test a form of machine learning live in a clinical procedure was, I don't know, that was a first for us. And I think I probably haven't seen that much else otherwise. And finally, some recent stuff. This was a work that was submitted and accepted to AUA this year. This was work done out of Pathology from Nathan Paulson and Tal Zevi in our group to predict adverse outcomes from pathology whole slide images. So given a cohort of patients that all had radical prostatectomy, could you predict from their digital pathology whether that person was going to have an adverse outcome? So this graph just shows that these two cohorts that were submitted for basically the training data of this algorithm were actually pretty similar in terms of their clinical values and what was seen. So the only difference really was some had adverse outcomes and others did not. So what we did was given a digitized pathology slide, we split this up into little tiny patches and we fed all these into this convolutional neural network. These things were all aggregated together and these were fed into a classifier. And the results were pretty interesting because we able to compare the predicted result versus the ground truth. And we get a receiver operating characteristic curve that's pretty good. So the AUC, I guess, was about 0.7. But this compares pretty favorably to other measures of like the CAPRA, I guess, prostate cancer risk assessment measures. In some cases, it does much better, and approaches at other levels fairly similar, but very exciting results. Digital pathology is a pretty ripe area for deep learning, and it's exciting that we're able to get some pretty great results this early on. So the final application that taking away from prostate cancer was some work that I was doing with Dr. Franco here. This was applying machine learning to uroflowmetry data in urodynamics. Now, this is a non-invasive form. It'd be great if we could get some more precise diagnostic interpretation from this data. But the challenge was that there's a lot of inter and intra reader reproducibility problems within this data. As you can see, this is data from 38 different subjects, but it's very noisy. I mean, taking a look at this, these are hard to interpret one thing from the next. Where there have been some measures, quantitative measures from Dr. Franco himself, like the flow index, to try to do that. But we wanted to see if we could do something directly from the data itself. So the approach basically started with, well, can we just standardize these uroflowmetry measurements? Well, the first step was smoothing these things out and making them look nicely. So we got rid of a lot of the noise in the data. And the second step was really, well, let's just put them all starting to a common starting point. So fine, we did that. Next was, well, what happens actually if we really take the volume out of the equation? So if we normalize by volume and we kind of align the back end of where these things are, that these flow curves to where they stop going, well, now these things are starting to look fairly similar. And you can see that over this population of data that things really follows distribution. And that distribution looks something like this, where you see the median flow curve. And this realization was fairly interesting, is that, wow, once we normalize, standardize this data, things actually follow a fairly consistent pattern. These are percentile bars here, really, of the middle 50. And I think that was 75 and 90 or so. But it really follows a fairly standard thing. And the question, I guess, previously was that, well, male and female flows, how different are they? Are they different? Well, by building up these two distributions and then comparing them, we see they're really not that different. And that was a fairly interesting, I guess, byproduct of this initial study that we were looking at, is that they seem to be about the same in terms of their flow patterns. And the idea, though, is now that you have a model of what is normal, I should qualify that those subjects, those small number of subjects, were deemed to be normal voiding subjects by Dr. Franco, which was an extremely painstaking task to go through all the data sets and say, wow, of all the ones that I've seen, these ones were the most normal ones we had. So that meant there was a high percentage of other ones that were abnormal flows. So what we want to do is say, well, you classify abnormal flows as some kind of deviation from normal now, once we have a model of normal. And there's a few different types of abnormal flow classes, but the idea is to, even just visually plotting these against the normal curve, you can get an idea of how abnormal someone is. This is providing these curves went through the same standardization process. A lot of them are actually fairly similar, and I'll show the next slide that the fractionated ones are hard to tell. But if you have these plateau type curves, which are characterized by this voiding where it just starts out slowly and then kind of just levels off in the middle and then drops off, well, you can tell that those are fairly abnormal fairly quickly from this visualization. And similar goes for these tower type flows, where it's a lot of flow at the beginning, and then it drops off rather quickly at the end. And you can see that that deviates very well from abnormal. And what we're looking to do now is quantify that. Is there a measure that can classify that directly rather than just a visualization? But the visualization itself is fairly clear. Now this goes into a dimensionality reduction. Now, again, this is performing unsupervised, basically trying to classify what these different flow types were based on training data. So actually the training normals, what we saw in that normal model were these blue triangles. And so we created this space of what normal flow is. And then we plot what all these different abnormal ones, along with some other normal circles, which are the test data for normals. And this really confirms basically what we saw in those visual pictures, was that fractionated flows are fairly difficult to distinguish from normal flows, and that some of the other types like plateau and towers do fall somewhat on the outside of the outskirts of this. So finally, to wrap up, machine learning in medicine, it really requires a lot of domain knowledge. It's clinicians are not anywhere going out of the loop in this, primarily because we can't do anything with this training data anyway unless you know what to do with it. And that really gets to, well, data is absolutely critical. So about 90% of any of these projects is spent probably just wrangling, organizing, and pre-processing this data. And these algorithms are only going to be as good as the data that they see. So the adage is, you put garbage in, you get garbage out. Well, that's absolutely true with this. And this is really compounded by the number of samples is critical. So if you are only able to give these things a small number of samples, well, that quality better be really, really good, or else you're not going to get very good results. And these motivations are really what's driving work in unsupervised learning, or working with weakly annotated data. So that's data that's either missing or not fully annotated, or stuff that just has rather than delineating the entire prostate, you just take the middle of it, or just some basic measurement of it, something that's quicker, less accurate, but maybe we can make it as useful as a full-blown annotation. And in medical, any kind of machine learning, the problem of generalization is really what would be the main limitation, I guess, in that really these algorithms are so over parameterized that they can overfit to the training data really, really well. And I want to offer an example that we experienced ourselves here. So this was an example from prostate gland segmentation. So this is what I showed you earlier. So we actually had 300 prostate images from Stanford and 300 from Yale. And naively, we trained this big deep learning network on just the Stanford data. And we said, oh, well, let's see how it works on the Yale data. So Stanford, we were getting great results, about 94% overlap. So that's just saying how well that the ground truth matched the prediction. And this was in 300 tests from Stanford, so we did great. We then took that same exact network that we trained from Stanford and applied it to just a Yale image. And that's actually a good example. On the median, out of 300 Yale ones, we actually got 0 overlap. The median value was 0. We did that poorly. And this is just an example of naively applying what you think might be a great algorithm trained on one thing. It might not work on the others. The reason for that is because both sites use different scanners. This is an example of the algorithm actually overlearned to the specific scanner at each site. Really, it's an intensity distribution, which we can correct for. So there's a difference in intensities of these images. So one just is a little bit different than the other. And we can correct for that. But this is the kind of things that you have to watch out for when you're doing machine learning in medicine. You want to avoid these kind of biases being baked into your algorithm. And I was fortunate enough to attend this 2019 workshop at NIH, where they're really trying to address these things. and some of the bigger goals, especially in medicine, are, can we establish trustworthiness and reproducibility in these machine learning solutions? The other things are something like explainability, interpretability. A lot of these algorithms get criticized as they're a black box. Well, that's absolutely valid. They are a black box. We have no idea what's going on under the hood. And a lot of research has been dedicated to trying to interpret what the results mean. So basically being able to say, like, why did an algorithm arrive at the answer that it did? Well, there's usability. It's how do these things fit within a clinical workflow? And then finally, there's these ideas of transparency and fairness. Is this algorithm biased in any way? For example, at Yale, if you train an algorithm that is based on a population, well, is that population representative of the general population, or are you just training to a specific demographic that might actually be biased? So very interesting questions. And FDA actually has some pretty good recommendations now, fairly mature now, about how artificial intelligence and machine learning can be classified as like software as a medical device. Finally, I would love to have any questions and hear from you and your thoughts. And my goal really, again, with this was to whet your appetite of what machine learning and artificial intelligence could do in urology. So these are just some preliminary work, but if you have any future ideas and would like to collaborate with me, please send me an email and I would love to talk. And I think there's a lot of potential for application in data science and machine learning. So thank you for your time and happy to take any questions right now.
John, this is Peter. Great talk, very interesting. And we're happy to have you in the department, and hopefully this is just the beginning. So let me just ask you a question. So I found the last study that you presented, Stanford versus Yale's segmentation of the prostate, interesting to me, because would argue that if the humans were looking at these, we wouldn't have the level of detection to depict that much of a difference between the two and would be able to interpret. But what was fascinating is that the machine learning algorithm that you used was so sensitive that it was able to recognize something that the human could not recognize. So I actually think it makes sense to me, and I think that just demonstrates the level of sensitivity that these algorithms can have compared to a human. So is that a misinterpretation?
No, it's both a feature and a bug, actually. You see, this is an example of the bug. Yes, they can be extremely sensitive. Yeah, any radiologist who just looked at these two images would say, yeah, they're both prostate, and they'd window these things to their liking and it would be no problem. They don't care about the absolute values of it. But the machine apparently quite does care about that. And to get an even more example that's even worse was that anecdotally I heard from a colleague somewhere else that given the same scanner that they had trained an algorithm and it worked really well. Well, then the manufacturer actually applied a software update to that same scanner, and that software update broke their algorithm because whatever it did to the underlying image just changed it that subtly that the algorithm had overtrained to that. So
does that mean, but does that, it's not a weak, but is this identifying or uncovering an aspect of imaging that may have clinical implications?
Well, that I think actually might be what the feature of this is. So the advantage would be if you're able to, if these things are so sensitive, you should be able to, it's difficult, but you can back out what the algorithm was actually basing its decision on. So it might be possible that, say, I mean, it's something that basically Daryl Martin and I are looking at in the department is like, given some kind of genomic information about that image, well, can you put an image in and can you get that genomic information out? But then can you go back and say, well, what led to that decision? Mm-hmm. Like what part of this image actually said, well, that some kind of lesion here that wasn't detected by a radiologist was what caused that decision to be made. And it could be that sensitive. You could also get something where you could learn that maybe all your features are doing, or it was picking up on some kind of like something totally irrelevant, which would be rather disappointing.
Right. That's what I was just going to say. I was going to say the difference between the two machines, either it can be something that's critically essential and that one is better than the other, or it could be just a red herring that you're going down a path that's not relevant.
Exactly. And that's really the drive for why we want interpretability, to say, what is this algorithm actually doing? That's the danger to the black box approach.
Mm-hmm. Thank you.
And thanks, John. This is Preston. That was a great talk. I mean, just going further on that, should not, or is it probably not, would the algorithm, or would we not be able to determine within the algorithm how to sort of standardize or be able to compare? I mean, I think you then looked at the Yale and Stanford data after balancing the intensities, but it seems like the algorithm should be able to automatically, once you've identified what needs to be sort of managed or averaged, do that.
That in itself would be a really great problem. Can you learn basically what the underlying information is? I mean, what's very interesting is it goes along with like computer question. I mean, there's a prostate's in there, a prostate's in both of these images. So can you actually teach the algorithm itself as part of can you learn what the best standardization is? Well, if you learn that, can you just say, well, what is the salient thing that makes a prostate? And can you take all the other like extraneous information out of that? And that's certainly an area that should be researched.
Hey, John, nice talk. It's Dr. Franco. I mean, basically, your problem with the prostates comes down to the same problem that we have with the uroflows, and that's creating the standardization and benchmarking sets that are necessary so that we can compare the same exact image or the same exact flow, because it's very clear that with the uroflows that different centers read different flows very differently, and if we don't create a benchmark, it then makes it very difficult. And I think that's probably the inherent thing, the most important thing in machine learning is creating those benchmarks. I mean, when you look at facial recognition, lighting has to be ideal. If not, once the lighting changes and shadows start to form on people's faces, that loses its ability to predict faces, and things fall apart. And I think it's just a matter of creating the proper benchmarks and to continue to work down the road and utilize them globally. That would probably advance us a lot faster down the road with these new technologies. Right.
No, absolutely. There's so much going on in terms of reproducibility is a big problem too in these. And again, there lies the problem. You can't like reproduce is challenging, but these algorithms, once you get them right, well, maybe they're more reproducible than humans in some of these cases. So really reducing the variance in that. It's especially around like some of this stuff in just image segmentation, as you add more and more data, you're really refining at the margins of the cases. You perform well even with a few hundred. Once you get 1,000, you're still performing on like average the same amount, but it's those like 90th percentile cases that's where you start seeing your performance increases. So it's really at the outliers you start getting better and better as more and more data you start seeing.
And just from a definition perspective, this is machine learning, and the next step into artificial intelligence that would be where the machine would actually be learning how to make these data sets or look at these data sets in a way that's interpretable so that we don't have to be doing the interpretation and creating them. I mean, is that
Correct.
a fair statement?
Absolutely. I mean, where the machine could start to reason itself, really. Again, these things are stupid right now because you have to tell them what to do. So in the sense, getting to that unsupervised learning is probably the most exciting area, because that's where you're starting to define things that you let the machine learn even more clusters than what you had already presupposed with your particular biases yourself. So you start getting new inferences that you never even thought of as a manual human expert rater.
Well, thank you so much, John. That was great. Really appreciate the talk.
Well, thank you everyone for listening. Again, if everyone has research ideas that they'd like to try, I am very open for collaboration. So,
All right, I think it's 8:31, so we'll conclude. John, thank you again. We appreciate it. Everyone have a nice holiday weekend. Take care.
great. Thank you, everyone.
Thank you.
Bye.
Thank you, John.